Assalamualaikum and very good morning to all of you. Welcome to our last class of this semester, and perhaps it's going to be your last class during your bachelor degree study in UMP. Okay, today I will talk about topic number 6 in our class, which is the wind effects on the structures. And here is the layout or the content of this topic, which we first will take a look on the wind and earthquake actions, and then we will move to the wind action on buildings, factors affecting the wind load, effect of roofing system, as well as the modern engineering approach for the tall buildings. Okay, let's take a look on the first subtopic, which is the wind and earthquake actions. Okay, we take a look on the mechanism of the load formation. So the wind load is formed based on the external forces, where the forces acting normal to the wind directions. Okay, and it is based on the pressures of the building surface, while the earthquake load, as you know, is the force which is based on the initial forces, okay, generated by initial forces which act within the volumes with the masses. Okay, and this is the difference between the wind load and the earthquake load. The wind load is based on the pressure on the surface of the building, while the earthquake load are generated from the ground movement and the initial forces of the building, which tries to resist the vibrations. Okay, and this is the effect of the lateral load, which is the wind and the earthquake. Okay, to the overall structural stability, it gives effect on the sliding, overturning, and the torsion or the twisting. So this is the explanations, okay, about all these three effects. Okay, which is the sliding. You can see here where the building slide, okay, on the ground, or the overturning, and as well as the twisting effect. And this is the structure. How we can prevent those failures, okay, how to prevent the overturning by wide or heavy footings, and how to prevent the twisting by cross bracing, rigid connections, and providing the shear walls, and how to provide the member failures by use more suitable member sizing. Then in the second subtopic is the wind actions on the buildings. Okay, the wind load is acting on the building for both pressure and suction. Okay, the wind load is always important for tall buildings, but it's also important for the low building. That's why we need the bracing. Okay, if the wind comes here directly, so it is positive pressure, and at the surface where the wind is not come directly, we call it as the negative pressure or the effect of suctions. And the suctions also affecting the roof, where the roof material can be going up, okay, due to the suction effect. Okay, and maybe we need to weight down the roof by using heavier materials. Okay. Okay, and also in this subtopic about the Malaysian windstorm events in the history, you already conducted all of this one. Okay, the damage causes by wind load and the engineering approach, you already conducted all of this in your assignment 2. So you can refer to your assignment 2 for your revision. Okay, and then the third subsection is the factors affecting the wind load. There are several factors affecting the wind load. Number one is the altitude and the building's height. Okay, here it is clear that the wind speed increases with the altitude. Therefore, higher buildings will experience higher wind pressure and will give higher load. as we can see here, as the altitude is rising, okay, from 500 feet to 100 feet and 150 to 500 feet to 1000 and up to 1500 feet, the value, okay, the magnitude of wind speed is increased, okay, from around 6 miles per hour up to 20 miles per hour. So the higher the buildings, the higher the wind pressure. Then the second factor is the terrain roughness. Okay, the wind speed decreases with the terrain roughness. The rougher the surface, the lower the wind speed, but it will create greater turbulence. As we can see here, okay, this is the surface of the Earth. What on the surface? Okay, we have the tall building, we have trees and single dwellings, and open water or open field. We can see here that at the similar altitude, let's say here is 250 feet altitude, okay, the speed, okay, the wind speed for the area full with tall building is about 5.7 miles per hour. However, at the same altitude, but with in the area or region with only trees or single dwellings, the wind speed can reach up to 9.5 miles per hour. And for the open field regions, at 250 feet, the speed can reach up to 14.9 miles per hour. So we can conclude that the rougher the space, the lower the wind speed, even at the similar altitude. Okay, here is the terrain category. We have 1, 2, 3, and 4 terrain categories. Okay, depend on the class and the surface from sea, smooth, open, very rough up to the chaotic. Okay, as you can see in this figure, and this is, you can read the landscape description here. And number 3, okay, factors number 3 is the shape of the buildings. Okay, we can see here that the boxy shapes and the streamline shapes give different response for the wind load. Okay, the boxy shapes building are exposed to higher wind load, while the streamline shape will result in lower wind load. Okay, we can see here in this figure 1 up to figure 4. Okay, this one is a boxy shaped building with square. This is boxy shaped with rectangular building, and this one is the circular and elliptical building. And we can see here that the wind intensity in both x and y directions, the highest is for this one. Okay, the highest is the highest pressure or the highest load is for this building shape. Okay, and the lowest is elliptical shape. Okay, due to the aerodynamic effect. Okay, so you can see here in this one, okay, the elliptical shape, so the wind will easily flow through the building. And then factor number 4 is the sheltered area. Okay, sheltered area. Area sheltered by mountains or buildings will experience lower wind load. So this is clear. So this for this part of, okay, this is open. Okay, also if let's say we have a house here. Okay, so this house will experience higher load compared to this house due to the shelter effect. Okay, and this okay, let's say this is the shelter by tree, and the wind come from here, and then it will go down, and we have a shelter zone where within this zone the wind speed is lower, and then it will speed up again after past the shelter zone. And topography also affecting the wind speed. where the hills and escarpment will generate sudden acceleration in wind speed, which result in higher wind load. Which you can see here that this is the hill area, and this is due to the escarpment. When the wind blow from here, okay, and then due to escarpment, it will do, it will create increment to the wind speed. Okay, we call it as a speed up effect. Okay, as we can see here, this is the wind blow from the sea, and then this is the shelter by tree. The magnitude is lower, and then due to the hill effect, okay, here the topography effect, okay, due to the hill, it will rise up, okay, the wind speed, and then here due to the shelter, the value is reduced, the wind speed is reduced again, and then it increase again due to the escarpment. Okay, let's take a look on the effect of a roofing system. Roofing system strongly influencing the performance against the wind load. It depends on the roof geometry and the inclination of the roof pitch. Okay, as you can see here, this is the traditional house in a rural area in Malaysia. Okay, we can see this is the typical roofing system. Okay, first one is the roof geometry. We have a lot of roof types such as the open gable, box gable, dormer, Dutch gable, mansard, sailbox, hip, gambrel, and so on. But for this level, I only will touch about the two types, which is the gable roof and the hip roof. Okay, which is here, this one, and also this one. Okay, the gable roof be the strong one in the shielding effect. However, the gable roof experience the worst effect compared to the hip roof. This is because the geometry can break corners and sharp edge. The use of hip roof can reduce the peak pressure as much as 50% compared to the gable roof. The hip roof recorded lesser suction compared to gable roof by reducing the peak suction around 42%. As you can see in this figure, you can see how the gable roof and the hip roof performance due to wind. If the wind comes from this direction, it will easily flow. But however, from this direction, it will be stuck by this wall. Okay, but for the hip roof, the wind flow will become more. The wind will flow easily. Okay, for both directions. That's why the hip roof is better than the gable roof. Okay, as you can see here, this is the pressure. Okay, the pressure analysis for both the gable roof and the hip roof. For the gable roof, you can see here at this corner, the pressure is quite high, between 5.6 to 6.5. That's why when we adjust the gable roof to become the hip roof, the pressure here can be lower down, okay, up to between 1.5 to 4.0 only. Okay, this is the difference between the pressure on hip roof and gable roof. And also the second one is the effect of roof pitch inclinations. It has significant effect on the wind flow around the building, where the roof pitch inclinations will cause increasing or decreasing of wind pressure on the building. An increase in the pitch of a hip roof cause increase in the workpiece suction. As the roof pitch increase, the recirculation regions behind the buildings becomes larger. So as you can see here in this figure, this is the difference between the roof inclinations of 15 degrees, 13 degrees, and 45 degrees, where you can see here that how the pressure becomes higher uh, as the roof inclinations becomes higher. And this is without turbulence, and this is the effect of turbulence. We can see as the degree of roof inclinations becomes higher, the area of turbulence also becomes larger. Okay, and for the last part is the modern engineering approach for the tall buildings. We have several methods to help the tall buildings in dealings with the wind actions. Okay, the first of all is the tune mass damper. The tune mass damper is a spring plus mass plus the damping device, which is installed on a primary system to lessen the dynamic response. The concept is frequency of damper is tuned to resonate out of phase with the vibration of primary structure. It leads to significant energy dissipation. Okay, the damper is a solid, okay, solid materials at the top of the building, and when the building sway to the right, the damper will act as a pendulum which move to the left, so it will cancel down the movement of the vibration. As the building sway to the left, the damper will move to the right. Okay, it is proven to be very effective in reducing the responses against the lateral load. For example, we have mass damper in KLCC Wind Tower, Taipei 101, and the Shanghai Tower. And okay, so you can see here several tall buildings in the world which use the tune mass damper to deal with the wind load. Okay, so this is the inside the Taipei 101. Okay, the floor. Okay, the top floor here, they produce a very huge solid mass damper, okay, which is, if I'm not mistaken, is equivalent to the 63 number of elephants. Okay, can you imagine, okay, how to put 63 numbers of elephants on the top of your building? Okay, it's formed with the solid steel. Okay, and the second one is we can use the tune liquid damper, which is effective in absorbing low frequency vibrations, and it is also cost effective and less maintenance and easily implementable. The concept is the frequency of damper is tuned to resonate out, okay, the energy. Okay, and this is based on the okay, a container with liquid to reduce vibrations of primary structure, which result in significant energy dissipations. Okay, sorry, this is the concept for the tune mass damper. Okay, so this is the, okay, so the concept is here. Okay, which is based on the sloshing and wave breaking, and the fundamental period of tune liquid damper should be close to the fundamental period of primary structure, where it can reduce up to 30% to 50% of the vibrations. So this is the concept of tune liquid damper, where we provide a large amount of liquid at the top of the building, so it will move in opposite directions as the movement of the main building. So if the building move to the right, so the liquid will move to the left. So just like we put, okay, this is the I mean the advantage of putting the water tank on the top of the building. So the water inside the tank can act as the liquid damper. Okay, it will stabilize the building during the vibrations. And the third method is by using the viscous damper, where the damping devices, it is a damping devices filled with the viscoelastic liquid as a medium. When subjected to the external load, the friction forces develop between different elements within the viscous damper. The friction force is generated to develop, okay, the friction forces generated among the molecules of the damping medium, among the shaft and the medium, and among the piston and the medium. It created, okay, the damping forces created acting 90 degrees out of phase with the displacement driven force. And here is the main advantages of using the viscous damper. First is its compactness, temperature insensitivity, the linear viscous response over a range of frequencies. It can reduce the wind-induced accelerations by 35%, and it dissipated around 60% of energy induced by the wind and small earthquake. And also, the viscous damper is significant in reduction the displacement and accelerations. Okay, here is the example of the implementations of viscous damper inside a building system. Okay, so the damper is small. Okay, so that's why this is the compact. So it reduce the use of space. Okay, this is the example during the installation, during the construction. Okay, you can see the position of the viscous damper. And the final one is we implement the belt thrusters and the outrigger. Effectively used, okay, the system is effectively used to control excessive drift caused by the lateral load, either by the wind or by the earthquake. Okay, it enhances the stiffness of the tall building where the T1 will be reduced. The external columns control core walls within with the very stiff structural elements. The bed outriggers here, this is the bed outriggers, ties the peripheral columns of a building. So this is the bed trusses. The bed trusses is will connecting the peripheral columns, and then the outrigger is the steel element, which connecting the bed trusses and columns to the main core. This is the main core of the building. The challenges is we will loss of space in the buildings if we implement this method of constructions. But however, it is proven to very effective in reducing the response due to the lateral load. Okay, that's all for this subtopic. Thank you very much for your kind attention. I hope you can do your best in your life and your future. That's all from me. Thank you very much.